Let's say we have an electromagnetic signal propagating through space. It moves like a wave with a wavelength, represented by a wave, and an oscillation frequency, f. The wavelength is the period in space, also known as the spatial period, of a waveform. It's the physical distance between one point on the wave and the next corresponding point. The frequency is the number of crests that pass a certain location in a given time. The crest is the peak part of the curve. The wave velocity, v, is the velocity at which the shape of the wave propagates in space. In this lesson, we calculate v based on the wave and f. You may be familiar with the idea of the period. We often use the letter t for the period. T is the time between two consecutive portions of a repeating curve. Wavelength, however, is a period in space. Note the horizontal axis is labeled x. In this example, wavelength equals 2 meters. Imagine sitting at a specific location on the x-axis. As the wave moves to the right, you record the height of the wave above the x-axis. At t equals 0 seconds, the height is the full positive value. At t equals 1 second, the wave has moved to the right, but we stay put. Our observation at t equals 1 second is a height which is still positive but less than the maximum. If we continue to observe the wave height, we will see it cycle through positive, negative, and back to positive values. The amount of time it takes to return to the value at t equals 0 seconds is the temporal period, or t. The figure starts to get busy, but the idea is the same. Continue making observations of the wave height from one particular location on the x-axis. In this example, it will take 8 seconds to get the same observed height you started with. Thus, the period, t, is 8 seconds. The frequency is the reciprocal of the period. Thus, f equals 1/8 hertz. Note, hertz, abbreviated hz, is 1 cycle per second. Can you visualize the wave moving to the right? See the green markings on the crest at t equals 0 seconds? This same green marking has moved 2 meters for the wave at t equals 8 seconds. Thus, the speed, v, is 2 meters in 8 seconds, or 1/4 of a meter in 1 second. The relationship between wave velocity, frequency, and wavelength is v equals f times lambda, where frequency, f, is measured in hertz. Wavelength is typically measured in meters using the metric system and in feet for the English system of units. Velocity, v, is measured in meters per second, or in feet per second, or in some other convenient combination of distance unit per time unit. More precisely, our equation is the speed of the wave, because velocity is a vector quantity specifying direction, as well as a magnitude. However, we commonly use the term wave velocity when actually we are describing the wave speed. Note, in the example, f equals 1/8 hertz, wavelength equals 2 meters. We observed a speed of 1/4 meters per second, which agrees with v equals wavelength, f equals 2 times 1/8 equals 1/4 meters per second. In free space, with no dielectric material to slow down the wave, the wave velocity of the electromagnetic wave is the speed of light. A dielectric is a material which supports an electric field while being a poor conductor of electricity. What our eyes perceive as blue light is an electromagnetic wave with a wavelength of approximately 475 nm. Remember, the n stands for nano, and is 10 to the power of -9. The frequency of this light is 630 terahertz. T stands for tera, and is 10 to the power of 12. Thus, the speed of this wave is what you're looking at on screen. In the second line, we replace f and wavelength with the numerical values. The units are omitted for simplicity, being careful to remember hertz times meters is cycles per second times meters, which is meters per seconds. Note cycles is a dimensionless quantity. 2.99 times 10 to the power of 8 meters per second is approximately 3 times 10 to the power of 8 meters per second. This is the speed of light in free space and is usually designated with the letter C.
What about propagation in a medium other than free space?
Coaxial cable is commonly used to connect a transmitter or receiver to an antenna. A coaxial cable has a core conductor surrounded by a shield conductor. These conductors are separated by a dielectric material like polyethylene. An electric magnetic wave propagating in a coaxial cable travels slower than the speed of light. For example, a radio wave of frequency 7 MHz has a wavelength of 34 meters when propagating through a length of coaxial cable. Let's calculate the wave velocity. This wave velocity is about 80% of the speed of light. This percentage is commonly referred to as the velocity factor, or VF, and is published by the manufacturer as a decimal number. In this example, the velocity factor would be published as 0.8. If we know the velocity factor, the wave velocity is v equals sub f times c. We'll try this example. Calculate the wave velocity in a coaxial cable with velocity factor 0.66. The wave travels slower in the coaxial material. To obtain the wave velocity, we multiply the speed of light by the velocity factor. Let's review what we've learned. The wavelength is the period in space, also known as the spatial period, of a waveform, and is the physical distance between one point on the wave and the next corresponding point. The frequency is the number of crests that pass a certain location in a given time. The crest is the peak part of the curve. The wave velocity, v, is the velocity at which the shape of the wave propagates in space. The period is the time between two consecutive portions of a repeating curve. Wavelength is represented by this wavelength symbol. Frequency is represented by f. Velocity is represented by v. And period is represented by t. The relationship between wave velocity, frequency, and wavelength is v equals f times lambda.